So we define our links like that. So we've got two joint variables. We've got two variables on our links. So we've got the variable A and we've got the variable alpha, which is 2 and 4. And we've got a joint, which again has two variables, D and theta. So any robot configuration can be defined by considering a joint link pair, which is a joint plus a link, and we move the reference frame between the joints and the links, and we give the solution of value of theta, d, a, and alpha, which sounds all right in principle and is actually fairly easy once you actually grasp it. So, let's have a look at this robot here. This is what we want to do. We want to find all the variables. So, we start at this point down here and work our way all the way through the joint links till we get to joint 5, or where that triangle or square thing is, which is the two interface. So we've got 5 joints, therefore we have 5 joint link pairs. You must appreciate that the robot has 5 and nothing more. You can't do it with 4, you can't do it with 6. Sometimes you get tempted to do it with 5, 4 and 6, but that will give you the wrong answer. So what we've got to do is quite simple. We start from the bottom and work our way through all the joints. It's very much like sort of taking this frame and putting this frame on one joint, then the next joint, then the next joint, then the next joint at the end. It's as simple as that. And the best way to do it is to do it exactly like that. To do it as a sort of totally mechanistic process. Don't worry about the fine detail. It's just from that point to that point to that point to that point, following a set of rules. And the rules are quite simple. Anywhere you've got to go along a link, you go along the x direction of the frame. Anywhere where you go along a joint, or where a joint is, the z-axis must point along the axis of that joint. It's as simple as that. So follow those two rules and you should not have any problem. Right. So, the final point to remember is that a link and a joint, in the sense of this kinematics, are abstractions. In other words, a link does not have to equate to a lump of steel in that robot. All right? And quite easily, a joint does not have to be just solely that rotation bit. It does have a displacement. So, that's the preamble. So, what does the answer call this? So, we start from the bottom, at this point here, that point there, and we work our way through from that point there to the next joint. Alright? So, and we've got to define for each of these is d, theta, a, alpha. So, you look at the diagram. Now remember, of course, this diagram the light blue diagram is drawn as the robot is in any given position. That is not the robot when all the thetas, all the alphas, etc. are zero. It's sort of a randomly drawn position. So what you'll get out of this analysis is not that, but something that can be moved to that position. Right, so we start at the bottom, and there's our z-axis, which equates to theta 1, and we've got to move from that point there to the top of that yellow line. Like that. Simple as that. Now, two things you've got to note. The little joints on here are not actually given a direction. In other words, you look at the arrows point with an arrowhead at either end, so it doesn't really matter which way the positive rotation at these joints is. In many examples, it does have that sort of degree of importance, but in this case, it doesn't. So, to get the frame to move from there to there, the value of D. Anybody can tell what the value of D is going to be? All right? You get the hang of this later on. D in this case is S1. So we're going from the bottom to the next joint. That's why I say don't get confused between what the mechanical structure looks like and the fact that it must be a link. In this case, the mechanical structure is in fact embodied within the joint. So we have a rotation at the top of alpha. Then depending whether or not it goes forwards or backwards, it could either be 90 or 270. In this case, it's 270. So we just do that simple rotation. So that means Z2 points along the axis of joint 2, and X2 points along where the next structural element is, or the next link is. There is no value of A, because this is one of these magic robots which are infinitely thin, so it's a totally planar system. So you got a value of D, value of theta. Now what's the value of theta? Anybody going to put that up on the parapet? What's theta? Oh, we'll get there. Theta is the joint variable. So we don't have a value for it. So theta is a variable. A, because we've got nothing along the x-axis, is 0. And alpha is that rotation of 273. It's as simple as that. Alright? Simple as that. So that will give us joint 1. All the 4 values of the joint link pair associated with joint 1. Right? Just bring that again to the attention. Right. Joint 2 and joint 3. These are the same. So we don't have to worry too much about them. So again, we're going from joint 2 to joint 3, from joint 3 to joint 4. And Zn is that direction. So we just sketch that out, and we put in the endpoints. So again, that Zn plus 1, in fact, this bottom should in fact be x n plus 1, but don't worry too much about that. Right, so what is this value of D? Is there any movement along the z-axis? There isn't any. So in both cases, the D's are in fact 0. Theta is your 2 variables, the joint 2 and joint 3. A is a dimension along that link, the yellow line, which is S2 and S3. S2 join 2, S3 join 3. There's no rotation around the x-axis, therefore the two values of alpha are 0. Right. So we've now got ourselves as far as there. Joint 4. Now joint 4, you look at it for the first time.
I'm sorry, but I don't understand what D, E, A and alpha are.
Sorry?
I don't understand what D, E, A and alpha are, because the way I see it, D isn't D just S1, S2, S3, and shouldn't that never change? I'm confused.
Right, let me go back then. That was slightly easier said than done. Right. Just go back. Right. Are you happy with that being the definition of a link? Now, the answer to that question is yes, I am, because that is the definition of a link. All right? So A is the distance between two joints, and D is the position or the distance between two links. As in that there. All right?
Okay.
Right? So, if we come to this one here, there's the base frame, there's the next frame. The distance between that frame and that frame is expressed along a z-axis. Right? That z-axis, therefore, is S1. Alright? Now that's why I said don't get confused between the structural elements in the robot and a length. Length and joint in this case are mathematical entities. Alright? So, let's go to this one. Now this one here, the motion or the direction of movement is along a x-axis. Therefore, that has a value A. All right. So you look at the robot and you say, well, there's a bit of steel between there and there, and a bit of steel between there and there. You would say, may say, sort of, as an engineering type of view, those are the links of that robot. What you should say is that's the structural element, and when you express it in kinematic links as a kinematic chain, those may in fact map either onto the z-axis or onto the x-axis, depending on how everything's orientated. All right? Does that help? Right.
So, is it just essentially the vector element on the z-axis that we map it to be the link?
No. The link is mapped onto the x-axis.
Okay,
The z-axis is the joint.
Okay, so is it just the projection onto the x-axis that we consider it to be the link?
Yes.
The structure? Okay.
Yes.
Okay.
Yeah. Right. Where right, joint 4. Right. Let me get. Right, now you look at joint 4, and you look at the little diagram here, and you realise that from joint 4 to joint 5 is interesting, to say the least. You say, well, I can do that by rotating around the y-axis. Do not let that thought ever enter your head. You cannot do that. The rules of this exercise says you cannot have any rotation or any movement along the y-axis. So, what you can do is this. is split it like that. And the important thing to remember is that theta 4 and theta 5 are both variables. So, that diagram I've drawn over here is that theta 4 and theta 5 are in a certain value, has a certain value of theta. So I can actually represent that by that top diagram. So there, this end here is your theta 4 and theta 5. Now you're immediately going to say that that does not look like that. Agreed? It does. Because remember, if I rotate around theta 4 by 90 degrees, I get that diagram there. So that's what you've got to remember, is that is just an artistic representation of the robot. It does not equate to any particular value of theta. So when you do it like that, it becomes quite simple. You again have a dimension d. What's the length along the joint? 0. So these two joints effectively in the kinematic model are at the same point. Theta, that's our variable. A, no motion along, in this case, along the x-axis. That's 0 as well. And alpha is 90. So that's why I keep saying that you've got to be very careful. In this case, the link length is 0, the joint displacement is 0. So you've just got to bear that in mind when you actually come to look at them. So some of these values may, first instance, you can say, I've got a link of length 0. It doesn't matter. Well, let's join that. And finally, joint 5, going along to the tool interface there, we just have a straightforward displacement along the d-axis and a variable theta 5. So, if you put that together, you get that. So that is a kinematic description, or description of the kinematic chain that that robot is built up on. All right? So, what I propose to do is, I'll say, that's it, that's how you do it. If you go into the blackboard which has the assessment, go to the assessment thing, there is a number of other robots that you've got to do the same thing for. So I'll let you do that yourselves, and then in about a week's time, I will come back and say, right, these are the ones which you have in that, so it says in-class test actually, but it's not really an in-class test. So you have those robots. Work out them for yourselves, and then we can go through them again, and we can learn from our errors. In addition, there's a little set of slides which is more of a, this is how I do it type. So this is how it leads you through the steps as a sort of a step-by-step guide. So we've now reached a point where I can actually now accurately describe that robot. What's the use of that? I've got to take it a stage further. I've got to take it from this diagram and get it to the full kinematic set of equations. So we've got to use transforms, etc. Right. So, kinematic equations, there's two bits to kinematics. There's actually a third bit, but we'll come on to that in a second. But we have four kinematics, that's the easy one. Ish. Given the link displacement to the adjoint angles, you push that into the equations you have. Tilt the handle, and out comes the position and orientation grain effector, or anywhere else in the robot. So that's fairly, inverted commas, easy to do as long as you multiply matrices together. The inverse kinematics is actually more useful. That's going from where you want to get to and what the joint angles have to be to get to that solution. This is the difficult bit. It's difficult because you're dealing with sines and cosines and arc sines and arc cosines, and those don't quite work out correctly. Depending on what you make for your first decision will in fact impact on all the other values. So we'll spend some time looking at the forward kinematics, and that will give you the sort of the basis. The inverse kinematics will do a bit of hand waving and say we can solve them by these various techniques, some of which are computational, some of which are analytic, and there's at least one approach which is totally random and based on neural networks, and so we don't quite know what comes out anyway. So those are the two approaches, forwards and backwards. So if we put it into this sort of relationship, is we have tool space. That only has 6 variables. Those are your linear positions and the rotation. So the tool has 6 variables. At the other end, we have joint space. We have n variables, i.e. how many joints there is in the robot. The important thing to remember is if you have less than 6, you may not be able to get to everywhere. If you've got more than 6, you actually end up with a solution which is in fact, you've got this redundant type of manipulated chain, which is a little bit more difficult to fathom. So there's forwards, there's inverse, and that's what we're trying to do. There's one stage further forward, and we'll come to that later on, is that will give you the joint variables. We go back one more, and that will give you the variables which you need to drive the motors to, the actuators to. And that's normally a straightforward transformation, which is fairly simple. But that depends on gearboxes, types of actuators, etc. So, we're talking about points in space. This is all this kinematics are leading up to. We're talking about a point in space. That point in space is the end point of the robot. Or, if you're doing a collision avoidance system, it being any point on the... Let's go. Oh. Funny time to have a test. Right. So, we've got this point in space. The point in space is that blob at the top, and that has 3 coordinates, A, B, and C. And you can say that is given by those, in fact, those column matrices. Normally, what we'll tend to work with is the N1, which is A, B, C, 1. That bottom one is the scaling factor. If you're doing a lot of CAD work, that is an important element because that's what's behind the scenes when you've got a CAD image and you're trying to replicate that into the real world. In robotics, that is 1. We've got to be dealing with real world situations. It is only 1, I'm sorry, it is only not 1 in one example, and that is when we're dealing with vision systems. Again, for the same point, we're mapping something which actually is magnified or reduced for an optical system. So, consider a point in space, which is, all right? Single link. Again, this should be fairly obvious. As we move that link around by theta, we change from L cos theta to L sin theta, and that gives the difference of the location, and the inverse is theta is cosine -1. You will note that as we go through various points, we do tend to lose ourselves, and that's something which will come up later on. Now, the important thing to remember, we've alluded to it very carefully by having this reference frame, this frame of reference which we take from the robot. When we're talking about a robotic system, that frame of reference occurs in more than one place. So we have our world. Most robotic systems are based in the real world, i.e. there's a reference frame in the real world. Then the robot itself has its own initial reference frame. All the joints have their reference frames. The tool has the reference frame. And finally, the part you're actually trying to locate may have its own local reference frame. So the real thing we've got to do is work out in a cohesive fashion and an easy fashion is how to get from one frame to the next frame to the next frame. And that is all we are doing. We've got to get some equations that will take us through that particular frame. I'm not quite sure what the set of 6 is. Don't slide 6 again. And we use this. We use a 4x4 matrix to describe any transformation. So to go from one frame to another frame, we can do it by using this particular matrix. It consists of 4 elements. It consists of a 3x3 rotational matrix here, submatrix. Come back to the bottom in a second. Px, Py, Pz are your position, or your translation, 0 and 1. Those really are scaling and other factors that can build in if need be. Any robot matrix that you come with will always have that 0, 0, 0, 1 as its bottom row. So if you're doing a bit of matrix multiplication for a robotic system and you don't get that across the bottom, you've done something wrong. It's simple as that. So it's a very good, simple, quick check to see whether or not you've got that multiplication actually correct. So the real question is, how do we actually put numbers into this? We put numbers in. The numbers that go in there are A, our alpha, our D's and our thetas. Those are the ones which go in there. But we actually make life a little bit easier for ourselves by, again, applying some sets of rules. So, consider the two frames, F1 and F2. Do disappear, there we are. There's F2. So the position of F1 and F2 is given by the coordinates P2. So any frame can be given a coordinate with reference to the previous frame. So we're stepping through, again, frame to frame to frame. And that will give its position. So we've got that, and also, as you'll see later on, that's a straightforward translational move. We actually have to rotate those frames relative to one another, and that will give you the rotations we require from theta and alpha. As long as we sort of do it against the right originating frame. So, as we noted earlier, using that matrix, there are nine rotational elements. So the actual rotation between two frames can be described as we're using 9 variables. I.e., it's the angle between the x 3 times, the y 3 times, and the z 3 times. It's instantly obvious that actually some of those are in fact redundant, because if you move by 90 degrees around one axis, it impacts immediately on the other 2 of that particular set. So it's not the fact that these are 9 unique numbers, these are in fact 9 fairly closely related numbers. And we use, in fact, they express the cosine of the angles, and they are called, for again reasons that we've got lost in the mists of time, LX, MX, NX, with the Y equivalents and the Z equivalents of PX, PY and PZ. Again, the bottom row is in fact 0001. To make life even easier, we only have to consider 4 cases. Actually, really, we only have to consider 3 cases because we don't really worry about the Y, but we put the Y in just to make it sort of nice and symmetrical. So only 4 cases are required for us to describe any motion we actually come across. And that is motion around the X, the Y and the Z axes, and actually a straight translation which doesn't require any rotation. So all we've got to do is map a particular motion onto that matrix, and that's the solution. So let's consider rotation around the x-axis. So we've got 2 frames. They are both, they're both centered at that point there. So the x, the origin of each frame is at that same point. So all we're doing is moving that frame relative to the x-axis. Like that. You will note that x1 and x2 are still collinear. The only angles of the change are between the y-axis and the z-axis. The angles between the new x and the new y and the z-axis do not change relative to the x-axis. So it makes life a lot simpler. So x2 and x1 are coincidents, so Lx equals 1, and x2 is given as that value there. So we actually will fill in this sort of column here. Filling it around on that one. X theta, and we're now getting something far more. So we're now looking at, we've looked at one axis, second axis, now the third axis, around the z-axis, gives us that, and there's no translation, so hopefully it comes out like that. So that there represents the matrix that describes us moving a point round the x-axis. So if I knew what the starting point was, moving theta around the x-axis, I apply that transformation, do the multiplication, and that will give me the new position. It's as simple as that. You do not have, by the way, to remember these per se. You don't have to commit these to memory. Right. So you now, that's one set. Let's do the other ones. And that will give us that. So that's all the translation and rotation matrices required. So it's very simple, at least at this level. Now we're still going to take the stage further to bring the robot back into the situation, but we're now got a set of tools that will describe the rotation around any axis and also the translation of the frame with reference to the old frame. So that is the core of robot kinematics. We've got to take the stage further to get to the A matrix, but that's something which is now fairly easy to take forward. But let's just play around with these for a second and see what we can do with them. Now, the important thing to remember is I've got 2 points here. I've rotated around the z-axis So we've got rotation around the z-axis is point U, 7321. That gives us that particular value there. We're rotating by 90 degrees. We repeat the exercise here by going around, taking this point B around the y-axis again by pi over 2, and that gives that solution there. Now, the important thing to note, and it should be fairly obvious to you because of the rules of matrix multiplication, if I change the direction of rotation, or the order of rotation particularly, I get a different solution. So, if I swap these two things over, from there to there, I get to a different place. That's fairly standard matrix, the rules of multiply matrices together. And we can show that, hopefully. So we start there, we've got a rotation round one axis, then round another axis. And we've got that point there. And if I repeat it, I get to that point there. And that is the other one. So, if you just sit down and just sketch it, it's fairly obvious. You go around one, then around the other, and the order is crucially important. So, by doing that, we've got start point there, we've got two concluding points there, different positions. Which does mean, if we go back to when we were talking about the robot 10 minutes ago, the order of rotation and the direction of rotation is, in fact, fairly important. And we've got to bear that in mind. So, if we actually move this frame, what happens to it? Now, what you actually can do, you can take a shortcut, a bit of an interesting shortcut, but something that, again, is relevant to kinematics. If you go back to the frames, we'll say put a frame there and put a frame there. I was not defining exactly what that frame was. So, I can say the frame actually consists of an origin and 3 unit vectors. So each length of each of the vectors which describe that frame, in fact, 1 unit long. That makes life a lot easier because we can find embedded in the solution slightly more information than we actually need, or we get slightly more information which we can use for other cases, etc. So we've got this translation of this point 4 minus 3, 7, and we'll rotate it around the z and the y, crunch some numbers, and that's what we actually get. And what we can say is the origin of the new frame is at 4 minus 3, 7. X, Y, and Z, i.e. points at the end of each of the unit vectors, will transform to those points. So you plot the whole lot together, and you get results. However, if you track the origin position from the end point of the new unit vectors, you actually get the orientation, i.e. that vector there, 0, 1, 0, 0, appears in the previous matrix. So the summation of that matrix means, or multiplication of that matrix means, you will get within that matrix both the origin and the orientations of the new vector, new unit vectors. So you've actually got the complete story from this very simple multiplication. That's what we need when we are looking at robotics. So there's the origin, there's the x, and that x says that the new x-axis is in fact parallel to the y-axis because that there is 1 and that is in fact 0 degrees, so it's parallel. So that's where we start off. We transform it. We don't transform it. Let's go back a bit. that's when it's transformed. So you see the X is parallel to the Y, the Z is parallel to the Y, and in fact the Z is parallel to the X. So just by looking at that matrix, you can actually get enough information to actually determine where everything is actually located. So we've now got a set of tools that will allow us to actually build up our solution to a robot. We've got to take this stage further. I'm going to just worry about this. What is, or more clearly, how is everything moving relative to each other? So, if you've got a reference frame, let's make the end of this bench to the reference frame. Normally, if I move across here, I'm moving with reference to that point there. However, there's another way of describing it. I say that the X, Y, and Z, I'm moving along the X-axis here. But remember, I've got a reference frame attached to me. And if that's so that's X and that's Y, I also say I'm moving in the Y direction of the moving frame. It gets a bit convoluted, but as long as you understand that you've got two frames and you can move either with reference to the fixed frame or the moving frame, you have no real problem. Because when we actually look at robots themselves, we're moving frames relative to moving frames, relative to moving frames that are in fact moving relative to a fixed frame. So you've got to get this sort of concept fairly closely sorted out. This is one of these sort of interesting definitions that you sort of look at and you go, yeah. I would just say this is a definition which you need to have in your notes, but once you grasp the idea of how you multiply the matrices together, you forget about it. If we got relative motion, we have a sequence of finite number of rotations. You've only got, with each frame, you've only got 3 possible rotations. The matrix multiplications do not compute, so you've got to get the order right. If you get the order wrong, you end up in the wrong place. So, if the rotating coordinate OU, origin with U, V, and W, is rotated by the principal axis of the OX with the original frame, you actually pre-multiply. And this just informs which way the order is. And the other way, if you're going around the other frame, you pulse multiply. So you've just got to get the order multiplication correct. However, to make your life easier, even though I've given you that definition, the matrix we have to use when we're talking about a robot, all this pre and post multiplication is actually embedded within that matrix. So you do need to know that how to form it, but once it's formed, you don't really worry about it. So that sort of sets the background. We are involved that we can actually put this lot together. So we've got that robot with its 4 variables for each joint and pair. We've got a kinematic set of tools which allow us to multiply various matrices together. And we say that it consists of a joint set of joint lengths, etc. And we can say, this is one of the things you used to state, that T2 equals the matrix product of A1 and A2. So you multiply those two together and you get T2. So A1 is position and orientation of the first link with reference to the origin, and A2 is the second link relative to the first link. The A matrix is the key to all robotic manipulation. So what we have to do is describe what the A matrix is. So I think we'll leave it at that point there. And so tomorrow, somewhere, I'll describe the A matrix that way.